1, Section 5 on infinite limits. This is the last section in Chapter 1. And infinite limits, pretty much just what the name indicates, in that we will be looking at limits that do not exist because they're either unbounded and increase without bound or decrease without bound. We're going to consider the function f of x equaling 1 over x minus 1. Now the graph, this is on my graphing calculator. It looks like it's all connected. But the line that's, the vertical line that's drawn here is the line x equals 1, which is not actually part of the graph. It is the vertical asymptote, because we know that we have a vertical asymptote at x equal 1 because I get 0 in the denominator. But what happens to the limit here as we approach it for this function if we approach x from the right or x from the left? Now, based on this graph, from the right side, it looks like it's unbounded and it's going to go up to positive infinity. Over here on the left side of 1, it's going to drop down and it's going to go to negative infinity. So we plug values in. Notice here a little bit smaller than 1, 0.5, 0.9, 0.99. And these numbers are getting absolute value-wise large, but they're negative. So it's going to negative infinity. Here from the right side, 1.5, 1.1, 1.01, the values are getting bigger positively and going to go to positive infinity. So that a limit in which f of x increases or decreases without bound as x approaches c is called an infinite limit. Now in this case, the limit as x approaches 1, not from the right, not from the left, but as x approaches 1, we don't say that that's an infinite limit. We just say that it doesn't exist because 1's going to positive. From the right, it was going to positive infinity. From the left, it was going to negative infinity. We'll talk about that in a second. Now, I have a really scary-looking definition here, and it's kind of an epsilon delta definition, except that there's no epsilon here, because the values are getting large without bound or getting small without bound. So an infinite limit, let f be a function that is defined for at every real number in some open interval containing c, except possibly it's c itself. The statement, the limit as x approaches c of f of x equals infinity, means that for all m, notice not an epsilon, capital M, which is usually thought of as a large positive number, for all m greater than 0, there exists, remember this means there exists a delta greater than 0 such that f of x is greater than m. So the closer we get to c, the larger f of x becomes. The larger our y value becomes, greater than m. So you pick an m, I can find one that's even bigger. Whenever, of course, this is small, when x minus c is less than some small positive number delta. Similarly, the statement the limit as x approaches c of f of x equals negative infinity means that for all n less than 0, now n would be a large, absolute value-wise large number, but negative number, negative a million, negative a billion, negative a trillion, there exists a delta greater than 0, small positive number greater than 0, such that f of x is less than n, smaller than this absolute value-wise large, but negative number, negative a million, negative a billion, negative a trillion. As long as x is very close to c, we keep it less than delta. So if I ask you to evaluate the following limits, let's get our graph here ready just in case. Let me graph and get this to be, because I just changed it slightly. Okay, here's my function, 1 over x minus 2. So I'll graph that, and you can see what the graph looks like. Very similar to the last one, except that my vertical asymptote's at 2. What happens as x approaches 2 from the right side? Well, as you can see on the graph, it goes to positive infinity. Think about this. Approaching 2 from the right side, here's 2. 2.1, 2.01, 2.00001, minus 2 is a very small positive number. 1 divided by small is big, and since it's positive divided by positive, it goes to positive infinity. Now you say, well, should I write down does not exist? Well, the limit does not exist, except that based on this definition, we can kind of state that it goes to infinity rather than writing d and e, because it kind of describes why it doesn't exist, that it's unbounded. The limit as x approaches 2 from the left side. Look over here from the left side. See how it drops down? Okay, a little bit smaller than 2, 1.9, 1.99, 1.99999. 1.99999 minus 2 is really close to 0 but negative. 1 divided by that kind of a number, small absolute value-wise but negative, is going to go to negative infinity. Now what about the two-sided limit? Well, as you can see, the limit from the right is one thing, the limit from the left is another thing. We don't write down plus or minus infinity, we just write down that it does not exist. Now, if I change this problem, let me go back to my function here, and let me sneak in a negative. So now I have this. As you can see in this one, and the one I covered up. If I graph this, it kind of reverses. From the left side, it's going upward. From the right side, it's dropping down. So as x approaches 2 from the right side, a little bit bigger than 2, 2.1, 2.01, 2.00001, this is going to give me a really small positive number. Negative divided by positive is negative, and this is going to be unbounded. This is going to go to negative infinity. Likewise, negative divided by negative, this is going to go to positive infinity. So again, the limit from the left is and the limit from the right are different values, so we'd say that it does not exist. Again, don't write down plus or minus infinity. I think you can see that a little bit there on my graph. All right, now here I provided a graph. I don't have an actual function here, but here I provided the graph, and I want to know what's going on here from the left side and from the right side. Well, from the left side, it's going to positive infinity. From the right side, it's going to positive infinity. So the two-sided limit, we say that it goes to positive infinity because these are the same. All right. Now also notice here that we have a vertical asymptote at x equals 2. So I'm thinking that if we have an infinite limit and we have a vertical asymptote, that somehow they go hand in hand, and there is a tie-in. In fact, this book defines, oh, can you see that all right? I almost think okay. We have tied in the idea, I hope anyway, with an infinite limit and a vertical asymptote. This is how this book defines it. So let me bring this over here and define the vertical asymptote. It says the line x equals a is a vertical asymptote of the graph of the function y equals f of x. Is either the limit from the right of f of x is either positive infinity or negative infinity, or the limit from the left of f of x is either positive infinity or negative infinity. Now, one of our favorite type of functions that typically have vertical asymptotes are the rational functions. So we're going to kind of look at those guys first, and then of course we have trig functions that have vertical asymptotes as well. Here's a theorem about vertical asymptotes. Let f and g be continuous on an open interval containing c. If f of c does not equal 0, and g of c equals 0, then there exists on an open interval containing c such that g of x is not equal to 0 for all x not equal to c in the interval. The graph of the function given by h of x equals f of x over g of x has a vertical asymptote at c. Now that's really what we've been calling, finding vertical asymptotes all the time. This is not equal to 0, but this does go to 0 at x equals c. Okay? So we have a vertical asymptote. Now, if I ask you to find vertical asymptotes, you do not have to try to rationalize each one with this theorem or with the definition, although if it asks you to show that, then definitely you would have to find and be able to use the definition to show that the limit from the right side, or the limit, if you see that, of course it sticks, the limit from the right side or the limit from the left side gives you infinity or negative infinity. I'll do that with this first example. But I'm going to find all my vertical asymptotes, and remember they're lines, so write them as equations. So x squared minus 1, my numerator is a constant, so I don't have to worry about it. This is equal to 0 at x equal 1 or negative 1. So I have vertical asymptotes here at x equal 1 and x equal negative 1. Now, if I ask for you to show that these are vertical asymptotes, I would take the limit as x approaches 1 of 3 over x squared minus 1. As x approaches 1, whether it's from the left or whether it's from the right here, let's go from the right side, just to make it easy. The right side a little bit bigger than 1, a little bit bigger than 1 squared minus 1. This is really, really close to 0 positive. 3 divided by that goes to positive infinity. If I wanted to take and find at negative 1, let's say x goes to negative 1. Let's do from the left side this time, of 3 all over x squared minus 1. As x goes to negative 1 from the left side, then what happens here negative 1.1, negative 1.01. Plug in, square it, really close to 1 but positive, minus 1, very close to 0 but positive. This is also going to go to positive infinity. So that would verify it, but if all they ask for you is the determinant, then this is good enough. Now in this case, in example B here, I take the denominator 2x plus 5, I set it equal to 0, I get x equals negative 5 halves. That's my vertical asymptote, and I'm sure that because negative 5 halves does not make my numerator 0, close, but does not make my numerator 0, x equal negative 5 halves. Right? Now again, if I wanted to verify this, then I would take the limit as x of g of x as x approaches negative 5 halves, either from the right side or from the left side, and show that I get an infinite limit. Okay? Now, h of x equals secant of x. Secant of x is 1 over the cosine of x. So the cosine of x is equal to 0 when x equals pi over 2 plus pi k, where k is an element of the integers. So where are my vertical asymptotes? My vertical asymptotes are all these values, infinitely many values. So my vertical asymptotes, I would write that as x equals pi over 2 plus pi k, where k is an element of the integers. Infinitely many. Okay, now let's go back to rationals like we had in part A and part B here. If the value of the numerator and the denominator at x equals c is equal to 0, then you have what we call the indeterminate form 0 over 0, and we get a hole in the graph, no vertical asymptote. You should remember that from your algebra days. Determine all vertical asymptotes of this graph. I'm going to factor both the numerator and the denominator. And as you can see, I have the same factor top and bottom of x minus 1. So when does my denominator equal 0? At negative 1 and at positive 1, but positive 1 also makes my numerator equal to 0. That's a hole in the graph. That's not a vertical asymptote, so be on the lookout for that. My vertical asymptote would be x equals negative 1. All right, let's look over here to some properties of infinite limits. All right, it says let c and l be real numbers. Let f, almost couldn't see that. And let the functions f and g be functions such that the limit as x approaches c of f of x equals infinity, and the limit as x approaches c of g of x is equal to l. So this one has a finite limit. Sums and differences. The limit as x approaches c of f of x, remember this is going to positive infinity, plus or minus g of x, which is going to l. Well, positive or infinity plus or minus a finite number is still going to go to positive infinity, no matter how big L is. L could be a googolplex, and this is still going to go to positive infinity. The products. The limit as x approaches c of f of x times g of x. Now this is going to infinity, and this is going to L. Well, this is be positive infinity if L is greater than 0. This would go to negative infinity if L is less than 0. And of course here, if g of x is going to L, f of x is going to positive infinity, I have a, quote, small number over a large number. This is going to go to 0. Always good things to remember these. All right, these properties also kind of hold, or very similar properties also hold for one-sided limits for functions as x approaches c, or for which functions, from the right to left, or for which functions as x approaches c goes to negative infinity. Very similar. So let's try 3. First guy up. As x approaches 0, now it doesn't matter whether it's approaching it from the right or from the left, because I am squaring it, this is going to be a really small positive number. 1 divided by really small is really big. 3 plus really big is really big. Now, I've evaluated that, and I put down my answer, and I've kind of explained it to you as I was writing it out. But if all you do is write down an answer and it's wrong, maybe it was supposed to be negative infinity, who knows? Whatever the mistake is, if all you have is an answer down with no explanation, it's going to be tough to give you partial credit. So make sure that on these kinds of problems, if you're evaluating, that you kind of maybe off to the side give a couple sentences to explain what you're doing. That way, if you've just made a silly mistake, I can give you the majority of the credit. Here, the limit as x approaches 1 from the left side of x squared plus 2 all over the cotangent of pi x. Now as x approaches 1 from the left side, so this is going to go to 3, 1 squared plus 2, this is going to go to 3. But as x approaches 1 from the left side, that would be like 0.9, 0.99, and so on. Remember what happens here at cotangent. Here's pi and here's 0. The cotangent, this is pi over 2, kind of does something like this, where I have a vertical asymptote there, I have a vertical asymptote there. So what's going on here? As x approaches 1 from the left side, this is going to drop down, and this is going to go to negative infinity. So I have a positive divided by a negative. This is going to negative infinity. Oh, hang on a second. I have a positive divided, if I pay attention to what I'm doing, this is going to negative infinity. I have 3 divided by absolute value-wise very small. This is going to go to 0 here. My apologies. Now cosecant, cotangent is cosine over sine. Secant is 1 over sine. So what we have here is we have the same kind of vertical asymptotes here. Here, let me write this, except that the graph looks a little bit different. The graph kind of does something more like this for a cosecant, and 5 times it's just going to stretch it out. So as x approaches 0 from the right side, this is going to go upward, and this is going to go to positive infinity. All right, be very careful. I almost got carried away on part B there, but I caught myself, which is fortunate, so I didn't tell you the wrong thing. And make sure that you give these a lot of problems, a lot of practice, work on your assignment, and then do a solid review before you take the Chapter 1 test. As always, practice, practice, practice.